the power of a foliar spray is you can put on nutrients that are measured in grams or a few kilograms per hectare and have a disproportionately large response on the soil microbiome and on the plants and the root exudates. So that's because you're harnessing the photosynthetic engine. You're putting on a small amount of energy to increase the photosynthetic engine and to increase that engine's output by 2 or 3x. And that's where the magic happens.
The Biological Farming Roundtable podcast helps farmers explore innovative, low-input, regenerative and profitable farming systems. The Biological Farming Roundtable is sponsored by Nutrisoil, an award-winning biological liquid fertiliser made from a big worm farm. Nutrisoil's purpose is to empower farmers to produce life-enriching food. My name is Nakala and I work at Nutrisoil. I envisage a future where farmers are rewarded for producing nutrient-rich foods and consumers have this easily available to them. Welcome to episode 41 of the Biological Farming Roundtable, the first of an exciting two-part series. This week, I'm joined by John Kempf, founder of Advancing Eco-Agriculture and a global pioneer in regenerative farming practices. John shares his insights into the plant health pyramid and the steps needed to build a thriving biological ecosystem. In part 1, we delve into the concept of passive immunity in plants. Learn how strategic nutrient management practices can unlock natural resistance to insects and diseases, transforming plant health and farming ecosystems. This is my conversation with John. Thank you for speaking with me today, John.
Why, Nakala, thanks for having me on. I've been looking forward to this conversation.
Wonderful. It was September 2020 when I last had you on the podcast. It was actually my most popular download. Last time we spoke in depth about your book, Quality Agriculture. This time I'd really like to explore your plant health pyramid, if you're okay with that.
Let's dig into it. That's quite a social compliment to be the most popular episode. Thank you.
By far, John. Absolutely by far. All right. So let's dig into this pyramid that you have developed. There's 4 stages of this pyramid that show each step that's needed to be achieved to reach vitality in a plant. The first 2 stages at the bottom of the pyramid are based on balancing your chemistry, and then the next 2 stages above are about having abundant and diverse biology to achieve plant health and vitality. So I'd like to go through each of those stages, and I've got some questions to kind of pull out the practicalities of that, if that's okay.
Absolutely. Sounds like fun.
All right. Well, let's start with stage 1. And that's about complete photosynthesis. Could you just briefly explain that stage to me, please?
Yeah, so the context for the pyramid as a whole is that at this point, I first developed this in 2011 and started just sketching it on marker boards and talking about it with farmers. It was quite interesting. We had one farm that we visited in 2011 where I sketched this diagram on a marker board, and I came back half a dozen years later, and they refused to let anyone erase them. Now the marker board was framed on the wall, and they refused to erase it because it had solved so many problems for them. So how the plant health pyramid came about was just the observation. Our early approach was really focusing on how do we manage plant nutrition to enhance immune systems so that crops are resistant to diseases and insects. And as we were experimenting and learning and using SAP analysis and just getting a lot of practical experience in the field we were getting experience in many different contexts and settings. At this point, we're working on about 50 different crops, all types of different environments, some very high humidity, some very low humidity. And what we started observing was this gradual development or evolution, if you will, of plant health, where plants were becoming to different becoming resistant to different groups of diseases and different groups of insects based on what seemed to be happening with nutritional balance and with microbial balance. And so that was the foundation of how we wanted to kind of describe what we were observing and provide a frame of reference for how we were thinking about it. So the foundational stage of the pyramid was based on the idea of photosynthesis is the only way we have of bringing new energy into an ecosystem. So if we want plants to be vibrantly healthy, if we want them to um, in order to be vibrantly healthy, they need to have abundant energy. And photosynthesis is the only way we have of bringing new energy into a system, new energy to plants, new energy into soil. And that matched up with our observation that when we grew these healthy plants that had high levels of photosynthesis, somehow they were rapidly building soil organic matter and building soil carbon levels while we were growing a crop. That crops were actually not extracting organic matter, but they were building organic matter. And what came from that realization, or from the homework that we did digging into this phenomena, was discovering that when plants have this ultimate ideal photosynthetic potential, let's just call it 100%. And for a plant to get to 100% of its photosynthetic potential, its genetic capability, requires an ideal environment. It requires perfect levels of moisture and lighting and carbon dioxide and temperatures. And obviously, that isn't a realistic expectation in an outdoor production agriculture environment. But it is realistic to expect to get to 30 to 40%, or in some cases, even as high as 60%. But instead, what is common is many plants are somewhere in the neighborhood of about 10 to 20% of their inherent photosynthetic capacity. And just a couple of weeks ago, someone sent me another recent publication, a white paper, peer reviewed paper that was published, describing how the excitement and the enthusiasm that they had discovered ways of genetically engineering and modifying the rubisco pathway, enzymatic pathway, and that they would be able to increase photosynthetic efficiency. And the article made me laugh because we are only we're only harnessing or only allowing plants to express a fraction of their currently existing photosynthetic efficiency. It's where plants are versus where they have the capacity to be. We're only at a shadow of what plants are really capable of. So the idea of genetically engineering another pathway is uh, is completely unnecessary and useless from my perspective. So this foundational level, level one of the plant health pyramid, came from the realization that actually it's not that difficult to go from the 10 or 15% photosynthetic efficiency that is common and double that to 20 to 30%. That's not an unrealistic expectation at all in outdoor production agriculture. And when you do that, when a plant produces double the sugar content in each day, each 24-hour photo period, if that can be sustained over the plant's entire life, that means it produces double the sugar content over its entire lifespan. And now some really interesting things start to happen. You start getting some very nice yield responses and some nice biomass responses. But even if you double the photosynthesis, it's unrealistic, and in most crops at least, to expect to get double the yield or to get double the plant biomass. So if it's true that the plant has doubled its sugar production, but it's not being reflected in biomass and or in yield, then where is it? Where does all the extra sugar go? And there's two interesting phenomena. One is that the energy density of each plant part increases, so you have more sugars and more fats concentrated in each section of stem or leaf or seeds. And the other phenomena is that a large part of these sugars, a greater proportion of these sugars, is sent out through the root systems and builds soil organic matter. So many of us have never really gotten to experience what plants with high levels of photosynthesis really look like and how they behave. The easiest way to say it is just simply that they begin behaving differently. Now, all of a sudden they have a surplus of energy, and that surplus of energy, plants begin expressing themselves. Their epigenetic expression changes in ways that are fascinating to observe.
You talk about non-reducing sugars in your pyramid. Could you explain to me what a
Yeah,
non-reducing sugar
so
is?
non-reducing sugars are the most simplistic form of sugars, of carbohydrates that cannot be further broken down and still remain as a sugar. So I struggle to remember which are which here, but if I recall correctly, I think glucose and fructose, if I remember correctly, are considered non-reducing sugars. So what would be considered reducing sugars would be starch, for example, starch which can be broken down into glucose molecules, which can then not further be broken down and still remain a sugar. So that is the way that I understand reducing versus non-reducing sugars. What is interesting is that um, these non-reducing sugars, these very soluble sugars, are a very attractive food source for many pathogens, many diseases, many insects require these very soluble sugars. But what happens is if the plant has nutritional integrity, if it has the enzyme cofactors that it needs, then the actual levels of reducing sugars, or excuse me, of non-reducing sugars in the plant sap will remain very low because the plant quickly converts that glucose and these highly soluble sugars into more complex forms, such as lignans and cellulose and hemicellulose and starches and et cetera, et cetera. And so what happens is you can actually have a plant. There's this interesting phenomena where the highest Brix content plants, the plants that have the highest overall total sugar content, if that high Brix reading is truly a reflection of health and not a reflection of drought or other weather conditions, then you can have very high Brix readings, but actually have very low levels of these soluble sugars in plant sap. Instead, the carbohydrates are much more complex in plant sap, which completely changes the disease susceptibility scenario.
Hmm. To achieve this complexity, there are some nutrients that are required. I think you list magnesium, iron, manganese, nitrogen, and phosphorus. At what stage should you be checking that a plant has these essential nutrients for photosynthesis and complexing these carbohydrates?
Well, in order to manage your crop really well for the long term, I would suggest that you need to understand where the levels are at all stages. And that's our approach has been to manage that with SAP analysis and measure it every 2 weeks of the growing season so we know exactly what the trends are and how good a job the soil biology is of delivering nutrients, how good a job that it is doing. But for certain, you need to know um, what the nutritional status of a plant is at any point where you are concerned about disease or insect susceptibility, because you can have a dramatic influence.
When you're trying to address these deficiencies, so you've used a SAT test, um, is there, like, I know that every plant has a nutritional requirement. What are your thoughts on delivering just a small amount of that nutritional requirement and if you've got good biology, or are you addressing the required amounts that's documented in grow notes? And I mean, that's what we use in Australia. So what I'm trying to ask is, do we give the plant everything it needs of these nutrients if it's deficient, or do we use smaller amounts with biological inputs or have biology active in our soil?
Yes, those are not mutually exclusive from my perspective, and so uh, the long term objective is, or even the midterm objective. It depends a lot, of course, on your local soil context, your soil health, and how rapidly your soil microbiome is regenerating, the crop mix that you have. There's a lot of variables that play in here, but um, our our goal, our intention is to develop a soil microbial system that can deliver 100% of the crop's nutritional requirement where possible. There are some geological contexts where there are some soils that just simply don't contain certain nutrients in adequate amounts where that needs to be addressed, but that's kind of a separate conversation. How this translates in practice is um, I have this as a result of our work on photosynthesis. I developed a very different perspective on the most rapid way of building soil organic matter. The I have the rather heretical point of view that the fastest way to build soil organic matter is to address whatever nutrients might not be an adequate supply as a foliar application of nutrients on a growing crop or on a cover crop. It's quite interesting. Um, about a dozen years ago, one of our more innovative fruit and vegetable growers began foliar feeding their cover crops. And within a few years, they said, we can't afford to not feed our cover crops because they get us, foliar feeding our cover crops gets us the greatest gain in building soil organic matter and the greatest improvements in our crop nutrition the following year. And then that that idea has now been adopted by mainstream commodity crop growers, broadacre growers, where the economics are very challenging, the margins are razor thin, and their assessment has been, in fact, one of the growers we work with spoke about this at a conference a couple of years ago, and he said, "I don't make money on my cash crops." Or what he was intending to communicate was, it's not my cash crops that determine whether I make money or not. It is the success that I have with my cover crops that determine whether I'm profitable or not. What he was communicating is that I can't afford not to foliar feed my cover crops. And so uh, I'm leaving out a few pieces of the story here, but you mentioned the five nutritional elements that we've found to be a fundamental requirement at this stage. And obviously, the other elements are also important, but if these five are not an adequate supply, then getting to level one simply will not happen. And um, of those five, two of those elements, iron and manganese, if they are deficient in plants, not in soil, if they're deficient in plants, practically the only practical way of providing them and shifting that profile is with a foliar application. And there's a bunch of biochemistry that is involved here, but the short version is that many of our agricultural soils are highly oxidized, including particularly in Australia, where you have many very weathered soils with lots of weathering and oxidation and environmental exposure over time. And so it's possible to have abundant, even surplus levels of iron in particular, less so for manganese, but it's possible to have high levels of these elements in our soils, and yet the crop is deficient or does not have an adequate supply. And that is a reflection of dysfunctional biology. Over time, and this can happen in a matter of a couple years, sometimes it takes longer, but over a period of time, as biology recovers, they can again begin delivering iron and manganese in adequate supply to the crop. But in the meantime, how do you build biology and how do you build organic carbon to sustain microbial populations? And in my opinion, the fastest way, one of the tools that allows us to build soil carbon the most rapidly and the least expensively, is a foliar application of nutrients on our crops. Because, as I mentioned a bit earlier, when we do a foliar application, if a plant is not yet at level one, if it's at level zero, and we put on a foliar application, we double the photosynthesis and the sugar production in each 24-hour photoperiod. When you do the math, there's variation, of course, based on crop type and overall biomass, etc. But it's quite realistic and quite achievable to generate multiple thousands of pounds of carbohydrates from the plant and transfer them into the soil. all for the cost of a foliar application that is, again, there's lots of variation in context here, but it can be as little as 10 to as much as $30 an acre, and sometimes in some unique contexts, it's with high value crops we go above and beyond that. But when you do the math, you cannot economically afford to put on carbon in any other form that is as efficient as a foliar application of nutrients that is specifically designed to increase photosynthetic efficiency. It's the least expensive carbon that you can put into the soil by quite a significant margin, and that's the long term. So I have this rather different perspective that the fastest way of building soil organic matter is with foliar sprays. And the key clarifier, the key qualifier here is that the foliar sprays have to be well designed. Um, it's been it's been true historically that if you speak to agronomists from, well, even agronomists today who are not designing foliar sprays this way, the perspective is that foliar applications are the fastest way of depleting the soil, and that can be true if they are designed. If foliar sprays are designed just to increase plant growth and to increase vegetative biomass without supporting the photosynthetic activity, it is absolutely possible for them to deplete a soil of nutrients and to deplete a soil of organic matter. But if they're well designed, they will not have that effect. They have the opposite effect. So it's quite fascinating to observe how when we use foliar applications to address manganese and iron, we get this dramatically different crop response from the one that most people are familiar with.
It's interesting, John. A lot of people, if they're using a cover crop, they might coat their seed with a biological stimulant, but they would assume that their cover crop exudates were in fact the fertilizer for that period. And I was just on a panel facilitating a panel at Grassroots in Australia with Joel Williams, and he talks about the fact that plant exudates are in fact biostimulants. So I guess when people are looking at their budget, they think, well, that's my biostimulant to increase my soil health. But what you're saying is it's so much more efficient if you're actually doing some type of nutrient application, foliar application on your cover crop as well.
I completely agree with Joel Williams. Think of it this way. Think of what he was describing. If you have root exudates serving as a biostimulant, what I'm describing is that with a well designed foliar application, not only can you increase the quality of those root exudates, but you can increase the quantity, the volume, by a matter of 3 to 5x and sometimes more. So, what is the effect of that biostimulant, those root exudates as a biostimulant? How much greater an effect can they have if you simply have a larger volume of sugars and biostimulants going out through the root system as root exudates? That's where the magic is. The power of a foliar spray is you can put on nutrients that are measured in grams or a few kilograms per hectare and have a disproportionately large response on the soil microbiome and on the plants and the root exudates. So that's because you're harnessing the photosynthetic engine. You're putting on a small amount of energy to increase the photosynthetic engine and to increase that engine's output by 2 or 3x. And that's where the magic happens.
Mm. The foliar application design in a cover crop, I imagine you would be needing to test each of the different plants so that you could actually get an idea of what's deficient in each plant or excess in each plant because each plant species is different. Would that be correct? Or do you just use the balance of the magnesium, iron, manganese, nitrogen, and phosphorus? Like, can you do a broad spray of that? What's in this design
Well,
process?
the context is that historically, when we have thought about designing foliar sprays, there have been two predominant approaches. One approach was let's put together a mix that produces the greatest plant growth response or vegetative growth response. So in those types of mixes, we commonly have different forms of nitrogen or Could be urea, could be amino acids, could be biostimulants. We have different ingredients that would go into a foliar designed to produce a growth response. Or a different way of saying it is that it's designed to trigger a specific plant physiological response. Sometimes we want to trigger a strong bloom or reproductive response. The second common thought process for designing foliars is to address deficiencies. Um, will take a tissue analysis or a sap analysis, and we'll add whatever is low. And neither of those two responses are necessarily wrong, but they don't produce the same crop effect if their prioritization is shifted to priority two of the design process instead of priority one. The first priority of putting together a foliar spray should be to say, let's address the nutrients that the plant perhaps does not have an adequate supply to achieve high levels of photosynthesis. So, the ones that we mentioned, nitrogen, magnesium, manganese, iron, phosphorus, the two that we see most broadly and most generally inadequate would be manganese and iron. And this is in spite of most agricultural soils having surplus levels of iron. And a similar, uh, I would suspect something similar is true in Australia of phosphorus, although phosphorus supply from mycorrhizal fungi and soil biology can work very well as well, even in low phosphorus soils. Um, and so the first step, let's say you have a tissue analysis and it shows that you are low in boron and zinc. And you look at the crop and you say, okay, I'm at a particular growth stage. I want to get some strong vegetative growth. So I'm going to put together a foliar application with some uh, urea, some liquid fish, some seaweed, and some zinc and some boron. It's reasonable to expect that you'll get a nice crop response from that. Um, but if you change things up and you say, and you do something similar, but you first look at it and say, okay, well, when I look at these other trace minerals, manganese is right on the edge of not being sufficient, and iron is on the edge of not being sufficient. And so my first priorities in the tank mix, I'm going to make sure that I address manganese. I'm going to make sure that I address iron, and it might be at very low rates. And then, in addition to that, I continue with my urea and seaweed and boron and zinc. But because I've addressed those two minerals that were needed for good photosynthesis that weren't present in adequate amounts, you completely change the result. You completely change the response to the foliar application. You get a much bigger response designing for photosynthesis as the first priority and addressing the deficiencies as the second priority rather than doing it in the reverse.
Okay, moving on to stage two. So we've addressed the stage one of complete photosynthesis. We're talking about complete protein synthesis. So stage two is about where soluble nitrogen compounds are converted into amino acids and complete proteins in every 24-hour photocycle. Firstly, John, can we establish what is a protein? Are they the same as secondary metabolites, hormones, and signaling products? Could you just clarify that before we start this section?
Well, the way that I think about proteins, what is a true protein, a complete protein, a healthily developed protein? Um, there are a few components to keep in mind. First, proteins are comprised of peptides, which are comprised of amino acids, which are comprised of sugar plus nitrogen. So you have various carbohydrates plus nitrogen in its various forms, aminitrogen, that is combined to form amino acids. Then these amino acids are bonded together in pairs of two or three that we refer to as dipeptides or tripeptides. And then those are bonded together to form these very long chain compounds that we call complete proteins. And I won't get into the stop amino acids, the sulfur bearing amino acids, but there is a critical component for sulfur for the stop amino acids in the protein coding in order to have a truly healthy complete protein. So, in short, complete proteins are very complex, long chain molecules that are quite stable in plants. And proteins in plants are they're largely inside the cell. They can also be outside plant cells, and they can be moved around wherever the plant needs them to some degree. This is why we see if plants are nitrogen deficient, they lose their green color, lose chlorophyll in one part of the leaf as the nitrogen gets translocated because nitrogen can move around and proteins can move around.
So if this stage is done effectively and these proteins are complete, can can they become un like can they become denatured, or can they unfold, and what causes that?
Yeah, so having a plant that has high concentrations or proportionately high levels of amino acids and amine nitrogen and nitrate and ammonium and so forth can occur in two ways. One pathway is there's simply too much in the soil, either from over application of fertilizer or manure or compost, or even in some cases from very aggressive microbial activity. It's not uncommon if we have cover crops or cover crop mixes that are dominated by legumes, uh, we large nitrogen releases from the breakdown and decomposition of legumes, or even from nodulation, can have a similar effect as nitrogen from a fertilizer, both on soil biology and on plants. So the one pathway is to to develop these high levels of these soluble nitrogen compounds is simply for the plant to be exposed to too much in the soil. It can come from fertilizer, lots of different places. The second pathway is if the plant does have high levels of complete proteins and has been manufacturing proteins well, it has had all the nutrients that it's needed. If that plant becomes exposed to a lot of stress, particularly high heat stress, when you have high heat stress, the plant switches from being photosynthesis dominant to being photorespiration dominant. You have more respiration occurring than you have photosynthesis. And this essentially shuts the photosynthesis process down. So it shuts down the production of sugars, and yet the plant still needs energy. So there's an interesting conversation that could be had here. But plants, given the option to do so, plants to some degree will first choose to use fats and lipids as an energy source if they have extra. Many plants don't. They don't have a surplus of energy stored as fats. And so, if they don't have extra energy stored as fats, they will next begin degrading proteins and breaking down proteins and extracting energy from proteins. So, as they begin breaking down proteins in a high heat environment, that results in the internal generation of these soluble nitrogen compounds inside plants, particularly ammonium. And this is why we have plants that we have some insects that we know that the pattern is they show up in high heat or dry or dusty environments like spider mites. And so we associate spider mites with those environmental conditions. But in fact, the spider mites are showing up as a reflection of the nutritional status of the plant relative to these various nitrogen compounds.
So heat and nitrogen can be causes of these proteins not being complete. Nitrogen being they can't form their complexity, and heat being and stress being that they can unfold them. Is that there are two things that we should be concerned about: is over application of nitrogen and maybe lack of cover on the soil?
Um, Well, this is a fascinating topic. I'm not talking about soil cover, although obviously soil cover is an important piece of it, but um, I'm talking about maintaining plants at a low leaf temperature. And this has been a very important observation for us, is that plant leaf temperature and air temperature are, first of all, they're not the same. Secondly, some plants are able to cool much more effectively than others, dependent on their nutritional status and their microbiome status. So it's possible to have um, two plants of the exact same genetics, the exact same variety, in different fields with different levels of nutritional balance and microbiome balance. And I'm used to thinking of this in Fahrenheit, so forgive me, you'll have to convert here. But it's not. It's quite common for us to observe as much as 12 to 15 degrees Fahrenheit nutrient variation between, let's say, a cherry tree in one block and a cherry tree in another block, even though the air temperature is identical. And this really matters a lot because the photorespiration process um, becomes dominant on C3 photosynthetic pathway plants, which is most of our agricultural plants. We also have the C4 plants, the worm season grasses. But for C3 plants, the threshold is 78 degrees Fahrenheit. Leaf temperature, not air temperature, but leaf temperature. Vibrantly healthy plants that have good photosynthesis, that have good nutritional integrity, that have a supporting microbiome, you can have air temperatures that are in the 90s, even into the low 100s, and still maintain leaf temperatures of 78 degrees because those plants are remarkably efficient at cooling. And there's this is a could be a whole conversation in and of itself, but the short version is that the healthier the plant is, the less water is required for cooling, which means a lot for drought resilience, and also the less heat stressed it is, and the less ammonium is produced inside the plant from uh, proteolysis, from protein breakdown as a result of heat stress. So there's some remarkable changes that happen when plants have a surplus level of energy and a good microbiome. Their drought resilience and their water use requirement completely changes through a number of different mechanisms.
And this is all achieved, even, I mean, we're at stage 2. I know there's stage 3 and 4, but really just having that correct balance of nutrients and a good microbial population in the soil, it can protect itself from heat stress.
In short, yes. There's a longer, more involved conversation, but coming back to what is happening here at level two, we found that um, in order to keep plants in this protein synthesis mode consistently, obviously we need to manage nitrogen levels. And just as a side note, I will say this: I think in agriculture we do ourselves a significant disservice by talking about nitrogen. We should remove that word from our lexicon because nitrogen does not exist in biological systems, or even in chemical ones for that matter. Instead, we should start having a more nuanced conversation about nitrate and ammonium and urea and amino acids and proteins because they are not the same. They do not produce similar responses in soil biology. They don't produce similar responses in plants. We actually, uh, talking about nitrogen in agriculture is as if though someone were building a house and call up the lumber yard and said, "Hey, I need a bunch of 2 bys with no specification on 2 by 4s or 6s or 8s or 10s, no specification as to the length. Just say, hey, bring me a pile of lumber. I'm going to build a house." We do ourselves a disservice by using this very loose language, and yet it's we all tend to do it. So obviously, we need to manage the levels of these various nitrogen compounds in soils. And then the other nutrients that need to be addressed are magnesium, sulfur, molybdenum, and boron. And the combination, when we make sure that plants have adequate levels of those 4 elements, and it has to be all 4 of them. A crop can have adequate levels of 3, but be low in 1. Let's say you have adequate or generous levels of magnesium and sulfur and boron, but you don't have enough molybdenum, you will still have insect susceptibility. You have to address all 4. And when you address all 4, our objective with our SAP analysis is to have a plant that has abundant levels of total nitrogen, which is one of the metrics in the lab. They measure total nitrogen content, but have nitrates and ammonium be at zero. So nitrate is measured at zero and ammonium is at zero, and yet we have abundant levels of total nitrogen. That is an expression of a plant that is quite likely, uh, I would even say is highly probable to be resistant to insects of many types. And in particular, um, uh, one thought that I want to go back to, the exception to this scenario is when we have very high chloride levels. If we have chloride levels that are higher than total nitrogen, we see a very strong relationship to insect susceptibility. So even if you address those four elements, but you still have high levels of chlorides, you will likely still have insect susceptibility. So it's possible to produce a remarkable degree of insect resistance simply by managing these nutrients at level 2 on the plant health pyramid.
So at this stage, we're still in managing the chemistry, and I know in the background it's always the biology, abundance and diversity as well. So if we have magnesium, sulfur, molybdenum, and boron sufficient, and the abundance and diversity of biology, and we're always missing some things, I know that. This is just a simple explanation. We should have no nitrates or ammonia left in the sap. What about free amino acids? Could you explain to me what the outcome of having excess amino acids in the sap is, and why that might be the case?
It was similar. It's related to my explanation of nitrate and ammonium metabolism. So the amino acids are one step further than that. When you have nitrates or ammonium gets converted to amine nitrogen, which then gets converted to amino acids. And if you have a surplus of free amino acids in the plant sap, um, it's likely to be a reflection of not having adequate levels of sulfur, or it can also be not having good enough photosynthesis, not having good enough levels of carbohydrates to convert those amino acids into peptides and proteins. So um, it could be summarized simply by saying that the nutritional balance, a nutrient balance, hasn't been addressed properly. And um, it's worth noting. You mentioned it, but these first two levels, level 1 and level 2, are simply a reflection of nutritional status, of nutritional integrity. It is possible. I'm not particularly a fan or an advocate for the use of hydroponic systems, but it is entirely possible to achieve level 1 and level 2 in a completely hydroponic system. It is purely a function of nutritional balance. Level 3 and level 4 are a slightly different story because they require very active biology. And that is also possible in a hydroponic system, but just very difficult the way most of them are managed.
So you could actually achieve complete protein synthesis and complete photosynthesis in quite a degraded soil, is what you're saying, John.
That's exactly right. In a very poor quality substrate, which means I don't want to antagonize anyone, but what that means is if they can do it hydroponically and you can't do it in your soil, then what does that say about your management decisions?
Absolutely. Thank you for joining me in part 1 of our podcast, Achieving Disease and Insect Resistance. It is exciting to learn that the first 2 steps of the plant health pyramid can be achieved by balancing chemistry and can occur in soils that are still not completely biologically active. Please join me next month for part 2 of our discussion with John, where you'll learn how to achieve active immunity with the support of biology. Please follow the Biological Farming Roundtable podcast. Share it with your friends and networks. I'm Nakala and I work at Nutrisoil, a liquid biological fertiliser made from a big worm farm whose purpose is to empower farmers to produce life-enriching food.